So looking at transformations of parent functions, the first thing you want to make sure you understand is what is the basic shape. All right, we always start with the parent function and then we look at how are we transforming that. Okay, so we want to double check that we have these basic shapes down. So a constant function would be something like y equals 2. Okay, just a plain number. What does it look like? Horizontal line. Okay, so we have a line here at 2. Make sure there are arrows on the ends of it. Okay. What's the next one? What's our next one? The identity function. What does that look like? Okay, equation would be y equals x. What does it look like? I see it on your papers. What does it look like? It is a line. Okay. What are some points on your line? 0, 0, 1, 1, 2, 2, right? Your x and y coordinates have to be the same. Y has to equal x. So we do have a diagonal line here. It's going to cut through quadrants 1 and 3. Okay. Next one, absolute value. So y equals the absolute value of x. What does that look like? It is a v. Where is the vertex of that v? Okay, so we have points like 0, 0. The absolute value of 1 is 1. The absolute value of 2 is 2. The absolute value of negative 1 would be positive 1. The absolute value of negative 2 would be positive 2. So we do get that v. What is the slope on this right side? Slope is 1. What's the slope on the left? A negative 1. So they're always opposite slopes, okay? The squaring function, what does that look like? It is a parabola. Okay, give me some points on our basic parent function, y equals x squared. 0, 0 again. 1, 1. 2, 4. 3, 9. Yes? How about the other side? Okay, just the mirror image, yes? So it should be symmetric to the y-axis. Okay, basic squaring function. How about square root? First of all, can we square root negative values? No, we'd get imaginary answers, right? We can't graph that when we're talking about just the real coordinate plane here. So we aren't going to see anything on this left side of our coordinate graph. Okay? The smallest number I can square root and get a real answer is 0. What's the square root of 0? Okay? What's the square root of 1? Do you know the square root of 2? Square root of 3? Square root of 4? We know the square root of 4 is 2. Oops. Helps to put it in the right spot. All right, how about the square root of 9? So what we end up with is an arch like that. I would be very specific on your graph, maybe make this really enlarged. That is the vertex of that, and that's the end point. Okay, your square root graph doesn't go beyond that. So it's kind of like half of our parabola, right? Just tipped on its side. Okay. Cubing function. Let's cube some numbers. What is 0 cubed? Okay, 1 cubed. 2 cubed. What's negative 1 cubed? Okay, negative 1. What's negative 2 cubed? So what we end up with is this twist. We refer to that as a cubic twist. Okay? And our last one, cube root. All right, so let's cube root some numbers. The cube root of 0 is still 0. The cube root of 1 is 1. The cube root of 8 would be 2. right? Cube root of 8 is 2. Cube root of negative 8 would be negative 2. Cube root of negative 1 is negative 1. So we still get this twist, but it's a sideways twist. Okay? Double check that on all of your pictures you put arrows on the ends because they do continue beyond what we've graphed. So when we look at transformations, we are going to start by identifying the parent function. What is the basic shape? Which of these graphs are we starting with? Okay? Now, in parentheses here, I just have x minus h. That could be absolute value bars around that x minus h. It could be a squaring. It could be a cubing. It could be all different kinds of functions. I'm just looking at kind of a generic one. What does the h do? It moved it left and right. Which way moved it left? Which way moved it right? That's the key. All right, so we are talking about a horizontal shift for h. It's going to slide our graph to the left or the right. If we see x minus h, which way does it go? Okay. So we're going to move to the right h units. If we see x plus h, which way does it go? All right. So the things inside with x are kind of opposite of what we initially think of. Okay? So if I had, say, an x minus 2, even though I see a negative 2 there, it's not going to negative 2, it's going to positive 2. Okay? If I saw an x plus 2, think of it like that. All right? So it's x minus negative 2, we would be going to negative 2. So inside moves are always opposite of what they initially look like. Okay. What does this k value on the end do? That's our up and down. Okay, vertical shift. So it moves up when we see what? Positive k. All right, and then it would move down when we have a negative k value. All right, so the outside thing, that k piece on the outside, is going to move just the way it looks like it should move. Positive moves up, negative moves down. Take a minute and adjust your notes from last Friday. If you need to add a few details, clarify any of the stuff we've just written down, go ahead and do that. All right, moving on. Reflections. We have two different types of reflections. We can reflect over the x-axis and we can reflect over the y-axis. All right, those are the two we're going to be looking at. What happens if the negative is in front of our function? Which way would it move? Okay, reflects across x-axis when the negative is out front. When the negative is inside, it's going to reflect or flip across the y-axis. Double check your notes. We've done a lot of reflecting over the x-axis over the years, not as much reflecting over the y-axis, but it is a possibility there. All right, and then the last thing that you looked at was stretching and compressing. Again, this first one, the vertical stretching and compressing, you've done more of that in the past. I don't know that you've done the horizontal ones. Okay, so we are looking at the a value, that number that's in front of whatever our parent function is. If a is bigger than 1, we would say we have a vertical stretch. Okay, means my y values are going to get bigger. Okay, I'm not changing the x coordinate, I'm just stretching the y coordinates and making them bigger. If our number is between 0 and 1, we are going to flatten out our graph. We're going to compress it vertically. And it is important that you write the word vertical in there, because we do have horizontal stretches and compressions. You need to make the distinction. What would happen if a was negative? We've accounted for the numbers from 0 to 1, and then the number is bigger than 1. What if it's negative? Then it goes back to what we had here. Okay, if that number in front of our function is negative, that's causing a reflection over the x-axis. So that first number is going to do two things. It's going to tell you if it reflects or not, and it's going to tell you if it stretches or compresses. All of that is vertical movement. Okay, what if A was exactly 1? Does it do anything? An A value of 1 would be your parent function. Think of all those graphs that we just did on your first page of your notes, right? Your A value on all of those was 1. Y equals 1x. Y equals 1 absolute value of x. Y equals 1x squared. If A is 1, we haven't done anything. That's our parent function. Okay? Then the last piece here is this horizontal. Now the number we're looking at is inside the parentheses, but right in front of the x. So it's different from our h value that's also inside parentheses. This one is right in front of the x. And anything inside the parentheses moves the opposite of what you think it should move. So just like our left and right movement was kind of opposite of what it looked like it should do, same thing with C. If C is between 0 and 1, it's going to cause a horizontal stretch. So the smaller the number, the bigger we move horizontally. Okay, we're pulling it horizontally. If C is bigger than 1, we have a horizontal compression. All right, so we are going to take all of these transformations and put them together. The first thing you always want to do is make sure that the equation is in this basic transformation format. Okay? So take a minute and write this down. If you have it in that form, you can always just move left to right. Identify all the transformations just as you read across it. Okay? So the first thing we would do is look at our A value. Are we stretching or compressing vertically? Are we reflecting over the x-axis? Okay? Then we look at our C value. If it's negative, we reflect over the y-axis. All right? If it's a bigger than 1 number, we're going to compress it horizontally. If it's between 0 and 1, we're going to stretch it horizontally. Then we look at our left and right movements, and then we look at our up and down. If you go in that order, you will always land in the right spot. Is it the only possible order you can do? No. But again, always going from left to right will land you where you should be. Any vertical movement, so that would be things like reflecting over the x-axis. It would be vertically stretching or compressing. It would be shifting things up and down. Those have to be done in a specific order. Okay? For example, let's say I have the point negative 2, 3. If I want to stretch that by 2, okay? Now I'm up at 6. I've made my y-coordinate twice as tall. Then I could reflect it over the x-axis, puts me down here at negative 6. And then if I move it up, I land there. Okay? That's different if I say I'm going to reflect it, then stretch it, and then move up. Or if I'm going to move up and then reflect and stretch. So the order that you do things in makes a difference. All right? So we are going to strictly go left to right. We'll always land in the right spot. All right, so it says identify the parent function, then the transformation, and then graph it. So ignore all the extra numbers. Focus on the parent function. What is happening right there? That little 2 means we're squaring it, right? The x is getting squared. So our parent function is y equals x squared. In your mind, what are you picturing? What shape? A parabola. So let's plot some points for our parabola, our parent function. 0, 0. All right, my board's really off. Give me a second here. Maybe not. All right, I think we're good now. So parent function points 0, 0, 1, 1, 2, 4, and then we can do the reflected version on the other side. Yes? I wouldn't draw that in. I wouldn't connect those dots because that's not our final graph. We're just using them to help us get to our final graph. Okay? What transformations are we going to do? What is this 5 going to move? Right 5, and then down 3. We agreeing with those? So we're going to take all of our points and just shift them right 5 and down 3. Now, with a parabola, we know that there's symmetry, right? So we could move half of our points and just reflect the other half over. All right, so let's start with our vertex. We're going to move right 5 and up 3. Whoops, sorry, down 3. Okay? Our 1, 1, right 5 and down 3. 2, 4, we're going to go right 5 and down 3. And again, you can use that idea of symmetry and reflect them over to get the other side. And then be sure and connect those with arrows on the ends. All right, let's try another one. What is our parent function? What is the parent function? What's happening to your x? We're cubing it, not cube root, but cubing. Yes? So we are picturing a y equals x cubed as our parent function. What did that look like? That's the twist one, yep. So our key points, 0, 0, 1, 1. I'm just picking numbers and cubing them, right? 2 cubed is 8. On the negative side, negative 1 cubed is negative 1, and negative 2 cubed would be negative 8. Again, I want you to get used to what those parent functions look like so that you aren't making a table of values every time. You know what points to graph. Now, how are we transforming that parent function? What's the 4 going to do? Left 4 and up 1. All right, so we're going to go left 4 and up 1. And we can just take each dot, move it left 4 and up 1. So we still have that same twist. We have just shifted it to the left and up. Okay. All right, parent function. First thing I see around my x is absolute value bars. So I'm going to start with parent function, y equals the absolute value of x. There are 3 things we are doing to this parent function. You can go ahead and graph your parent function points. Remember, this is a v, so 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. What's the first thing we do? What's the very first thing you see in that equation? Yeah, there's a negative. That negative means we are going to reflect over the x-axis. Okay, what's the next thing we're going to do? All right, right 2. Somebody else, last thing? Up 5. Okay, so if we take our v and we reflect it over the x-axis, we're going to get an upside down v. Yes? Each of our points, I'm going to go through and move those same 3 transformations. So I'm going to start with my vertex. What happens when you reflect a point that's on the line of reflection? It stays there. Think back to your geometry days, right? So the vertex 0, 0 isn't going to move with the reflection part. But I can move it right 2 and up 5. All right, I'm going to make that a little bit larger because I do want to emphasize where that vertex is. Now let's take the point 1, 1. We're going to reflect it over the x-axis. If I do that, it lands down here at 1, negative 1. All right, then I have to move it right 2 and up 5. If I take the point 2, 2, reflect it over the x-axis, now I'm down here at negative 2, and then I'm going to go right 2 and up 5. Does that look correct from our vertex? Should we see points moving down like that? Okay. So that is the right side of my V. Now I can do the same thing on the other side. The point negative 1, 1, reflected over the x-axis, and then right 2, up 5. The point negative 2, 2, reflected over the x-axis, right 2, up 5. And I get the other side of my V. Okay? Now, both the parabola, the x squared graph, and the absolute value of x are symmetric to the y-axis. So if you know what one side of it looks like, you should be able to just flip the other side over, that line of symmetry. The other thing that's kind of special about absolute value graphs is the number in front, in this case it's just a negative 1, that represents the slope of the right half of your V. So look at our final red graph here. Do we have a slope of negative 1? Yes? And then on the other side, it would just be a positive 1 slope. It's just the opposite sign. All right, so down and back gets me, or up and right, gets me a positive 1 slope. So that's kind of a quick way to graph. If you know where your vertex is, and your vertex moved based on this, right? Then you can use that front number for the slope of the right-hand side. All right, looking at number 4. What is the 1/2 in front going to do? It's going to compress it now. Remember I said you have to say vertical or horizontal? Right, because we have both types of compressions. So is this vertical or horizontal compression? Vertical. All right. So we have a vertical compression of 1/2. In other words, we're going to scrunch everything down, right? Squish it down. What is the 3 going to do? Okay. And somebody else. The 4? Up 4? Okay. It's an absolute value graph, correct? So we are picturing our V. All right, so get our parent function points plotted. We are going to compress that. So instead of our V being this steep, we're going to flatten it out. Remember we said that the front value here is going to represent the slope on the right side. So instead of having a slope of 1, we're going to have a slope of 1/2. Right? It's going to be more gradual. So let's go ahead and take our points as if we were going to graph it with the transformations. We're going to compress things. That means our y coordinate is multiplied by 1/2. So whatever your y value is, you're going to just make it half as tall. Well, what's half of 0? Still 0. So that compression doesn't affect the vertex here at 0, 0. We still can move it right 3 and then up 4. Okay, that's going to be the new vertex. The point that's at 1, 1, if I compress it to half its size, now it's at 1, 1/2. Okay, it's only halfway up. And then I'm going to move it right 3 and up 4. The point that's at 2, 2. If I compress it to half its height, now it's going to be at 2, 1. And then right 3 and up 4. That is the right side of my V. Does it look like the slope of that piece is a 1/2? Up 1 over 2? Yes? So on the other side, I can go up 1 and back 2 to get that branch. Okay, it's just the opposite. That would have a slope of negative 1/2. So for absolute value graphs, I would use the idea of the slope piece. It's going to make it faster than transforming all of those points. So find where your vertex moves, which again is going to be based on that, and then use this as your slope. Okay? But make sure it's the slope on the right side. All right, we have one left. What is the parent function? What's happening to the x? It's getting cubed. All right, so our parent function is a cube graph. So again, 0, 0, 1, 1, 2, 8. And then on the left side, negative 1, and negative 2, negative 8. All right, what are we doing to those points? How are we transforming that? The 2 in front is going to do what? It's not inside being cubed, right? It's on the outside still. That's an A value. What does an A value of 2 do? Outside things affect vertical movement. So it's going to be a stretch, a vertical stretch of 2. And then the minus 5, is that inside the cubing piece or is it outside? It's outside, which means that's my K value, which moves it down 5. All right. So we are taking all of these points and we are going to make them twice as tall. All right, let's start with the one on the right here, the 2, 8 point. If I make this twice as tall, it's now going to be at 2, 16. Does that make sense? I've stretched it. I've made it twice as tall. My y-coordinate gets multiplied by 2. So now I'm up here at 2, 16. And then I have to shift down 5, which means I'm going to land at 11. Okay. This next point, all right, the 1, 1. If I make it twice as tall, it's now up here at 2 instead of at 1. And then I have to move it down 5. Okay. The center, the origin here, 0, 0. Timesing by 2, 0 times 2 is still 0, but down 5. Okay. Our next point here, negative 1, negative 1. Doubling it puts me down here at negative 2, and then down 5. My last point is at a negative 8. If I double it, now I'm at negative 16. And then if I move down 5, I'm at what? Negative 23. So I'm way down here, right? Off our graph, but we can still aim for that value. So we have this kind of shape. So it still is that same cubic twist, but it's been stretched. So it looks a little skinnier than normal. Okay. Questions on any of the parent functions? So are we able to identify the parent function? Do we know the shape of those parent functions? Okay. Can we identify the transformations? And then can we move those? Yes? All right. We'll look at some more complicated transformations tomorrow. For today, your assignment is on page 283. You're going to do 59 to 79 odd. You can skip question 73. 81 to 95 odd, 103, 107, and 109. All of this can be done on graph paper. I will get that passed out to you.